9 o'clock p.m. here in Arizona. So welcome everyone to Lowell Observatory's live stream of Jupiter and Pluto's opposition. And we'll be doing some interactive stargazing. All right, so it's just about 9 o'clock here in Arizona. I'd like to welcome everyone from all around the world to tune into our live stream of Jupiter and Pluto's opposition. We'll throw in some interactive stargazing throughout this program as well. But again, welcome everyone, and I want to thank you for joining us. So my name is Emery Littlefield. I've been with Lowell Observatory for about 5 years. And unfortunately, with COVID, we've been transitioning into more of this digital presence. But as soon as our doors open back up, anyone is welcome to come and actually see some of this stuff in person here at Lowell Observatory. So without further ado, we'll talk about what that thing is. So the oppositions that I mentioned, what's happening with Jupiter and Pluto both right now, is that if you imagine our solar system kind of all splayed out with the sun in the center and each of the planets kind of forming their orbital ring around that. Right now, Earth is on one side of the sun. So let's say the sun is here, Earth is out here, and Pluto and Jupiter are both actually in line directly opposite in the sun from us. So that's why we would call it an opposition. It's directly opposing the sun from us. Also means that it's the closest they can possibly be to the Earth. And that means it's probably the biggest and best time to view this object. So we'll go ahead and look at those. At some point, I don't know if we were able to get it yet, there will be a video of Jupiter through our historic Clark telescope up at Lowell Observatory. So that will actually be a live view of what you would be able to see if you came up to our observatory once we open back up. So there's a lot of history at Lowell Observatory. We've been operating in Flagstaff since 1894. That's actually before the city of Flagstaff, or actually before Arizona came a state and right after Flagstaff became a city. And so we're talking about a lot of history here. The Clark telescope was built in Boston, transported out here to Flagstaff by train. And in fact, talking about these oppositions, we even moved the Clark telescope all the way down to Mexico to view Mars at its opposition. So back in 1896, we had just gotten the Clark telescope into place. We've got, a big winter storm coming through, and Percival Lowell decided to take that whole telescope and move it down to Mexico. So we actually have a picture of that, if we could bring up, where when the Clark telescope was down in Mexico, again, that happened very soon after we first brought it there. That telescope dome that you can see in that image is the same dome that's here in Flagstaff. So they assembled it in Mexico, brought it back here to Flagstaff. and you can see all that there. Now, a couple of other things that have happened with that Clark telescope. We used it to take the spectra of distant galaxies and discovered the expansion of the universe here. So we also have another picture, and that one shows a man named Vesto Melvin Slifer standing at that same Clark telescope and viewing an object, maybe the Andromeda galaxy or another distant galaxy, and actually noticing their speeds. Maybe they're coming towards us or away from us. But either way, yeah, very, very interesting things that have happened with this Clark telescope. We'll view a video later on made by our wonderful historian, Kevin Schindler, and that will be taking place inside of the Clark telescope. So you'll get a chance to tour that, where that view of Jupiter is coming from right now. And you'll also get a chance to learn a little bit more about that fellow Vesto Melvin Slifer. So with that being said, Lowell Observatory as a very, long-standing observational institution here in Flagstaff, Arizona, we can talk a little bit about Jupiter and Pluto, since those are going to be the objects in focus tonight. So Jupiter, the largest of the planets in the solar system, has lots and lots of moons. In fact, we've been discovering them almost, every year since the beginning of astronomy. So one of the first things to be looked at through a telescope was Jupiter back in the early days. 1610, Galileo designed a telescope that he was able to see the sky with. And Jupiter was one of the first things that came into focus for him. And he actually ended up discovering a series of moons around Jupiter. And those were moving, and he was able to put together the dots that not necessarily everything in our solar system is going to go around the Earth. He was noticing that far out in the universe, far out in the solar system, there were actually other objects orbiting Jupiter. So that was just some observational data to support the view of the heliocentric model. And that's a really interesting part of astronomy and how we see things. So as for Pluto, that has a very special place in our hearts here at Lowell Observatory and in Flagstaff in general, since it was discovered here back in 1930 by a man named Clyde Tombaugh. Now, that we'll go into a little bit more later on as well. We have some pictures and demonstrations of how Pluto was found. But before we do that, we still have, Lowell Observatory still has a legacy connected to Pluto. And that involves Dr. Will Grundy. So we could bring up a photograph of him. He's sitting next to a small model of a spacecraft called the New Horizons probe. And that went all the way out to Pluto. Took about 9 years to get there, traveling very fast, one of the fastest things to ever leave the Earth, in fact, about 36,000 miles per hour by the time it got near Pluto. So we're looking at a long legacy of science with Pluto. That mission is currently still sending back information on the outer solar system. Dr. Grundy is interested in the infrared wavelengths being collected by an imager on that New Horizons spacecraft. And he actually does a lot of work with ices, not necessarily water ice, but things like methane ice and nitrogen ice. And so we'll actually be able to tie that into Dr. Hanley's presentation coming up in a moment here too. So we do have one of our very own Lowell astronomers, not only Dr. Will Grundy looking at Pluto and the ices that form there, but another Dr. Jennifer Hanley studying the ices all across the solar system, not just limited to out there, but places like Mars, as we'll see some of the moons of Jupiter as well. So that's going to cover most of the objects that we'll be focusing on tonight. Of course, during our interactive stargazing happening a little bit later on, 2 separate chunks, guests and viewers can actually look at whatever they want. So you feel free in about 20 minutes. You'll be welcome to go ahead and give me some ideas on what to look at. So without further ado, I did mention that we have Dr. Jennifer Hanley available to talk about some of her research on the ices on Jupiter's moons. And so if we want to go ahead and kind of work our way into that would be great. Dr. Hanley, are you ready to go?
Yes, I am. Thanks, Emery, for that introduction. So tonight, I'm going to talk a little bit about Jupiter's iciest moon, Europa. It's a pretty interesting moon. As Emery mentioned, it's one of the 4 Galilean satellites that Galileo saw in his telescope. It is the second in from Jupiter, and it's about the size of our own moon, so it's very similar in size, but it's covered in water ice. And you can see here this image shows a lot of reddish material along with the whiter, more water ice stuff, which I'll talk a little bit more about how we know that. So first I wanted to give a brief history about the exploration of Europa and Jupiter, of course, as well. So the first flyby of Europa and Jupiter was Pioneers 10 and 11 in 1973 and 74. You can see here that the image is pretty blurry, actually. And this is the best image that Pioneer 10 got. Basically, it could tell us that, well, there's some dark spots and some brighter spots. And that's about as well as Pioneer 11 did as well. We got much better detail with the Voyager missions. So Voyager 1 flew by in March of 1979. And you can start to see some of these lines across the surface. And Voyager 2, in fact, really got some nice images of the lineae, as we call them, the lines, in July of 1979. So we started to get better images, as time goes on and as technology improves. But all these missions were flybys. Finally, almost 20 years after the Voyagers, Galileo went, and it's a spacecraft that was orbiting Jupiter. So it was a mission to look at the whole Jupiter system, Jupiter and its moons. But it did focus on Europa a lot because it's such an interesting moon from an astrobiological perspective. It has this water ice shell. Galileo confirmed, or I guess discovered, that there is a subsurface water ice, a subsurface liquid water ocean beneath the water ice. And so we really are interested in what the surface material is composed of. What is the subsurface ocean composed of? Is there any interaction between the crust and the subsurface ocean? And are those conditions favorable for life? So during that time, Cassini, which you might recall was a spacecraft that went and orbited Saturn. It flew by Jupiter using it as a slingshot, as an acceleration gravity assist. And this is just such a cool video. It's actually an animation of a few different images put together, but we have Jupiter in the background, and we have Io and Europa together. So as Cassini is moving past it, we see the two smallest moons. So another flyby that happened was the New Horizons flyby that went to Pluto, the Pluto system, and that flew by in 2007. And on the right here, we have, again, an animation of multiple still images put together of Europa taken by New Horizons. Oops. too fast. Okay, right. So next is Juno. So Juno is actually a current spacecraft orbiting Jupiter. It arrived in 2016. It is a mission designed to study Jupiter, though. So it really is on a tight orbit around Jupiter, and its focus is not the moons. Here is an image of Jupiter and Ion Europa. And it's still, just because it's looking at Jupiter or only designed to study Jupiter doesn't mean that the scientists aren't going to try and see what they can get out of it. So this is a pretty cool video, I think. This is Juno taking some images upon approach to Jupiter. So here it is zoomed in by 2, and you can see the moons. In fact, here's Europa, this one on the left of Jupiter here, and it's coming in. It's about to go through the shadow of Jupiter. You see the sun is coming from the right, and it pops back into view after it comes out of Jupiter's shadow. So I'll just play that again really quick. So here's the full view of it. And one thing I think is interesting is, you know, this is what it would look like in real life. You know, you look at those, you know, space movies and space TV shows and come up upon a planet and it's just huge. Planets are relatively small in the vastness of space. So as you're coming up upon it, it's still pretty small until you're really close to it. So let's see. Oh, next slide. Okay, so we haven't actually had a mission that was designated just to look at Europa, but that might change soon. There's currently plans to launch a new spacecraft called Europa Clipper. Tentative launch date 2023, and then it would take some time to get there, of course. And this would be a mission solely to look at Europa. Of course, again, you will be looking at other things too, but really all the instruments and everything, the orbit, the trajectory, everything's designed to look at Europa. So I'm very excited for that. So if we talk a little bit more about some of the results that have come out of these missions and some research that's currently being done, here's a image from the Galileo near-infrared mapping spectrometer. So, you know, we talked about cameras. Well, cameras typically look at visible light. That's what we would see, but cameras can take pictures in other wavelengths. And so that's what this is doing here. We have a picture of Europa in a different wavelength region. And so this is the near-infrared. And again, Emery mentioned, you know, that's kind of interest of some of us at Lowell. It's a really helpful wavelength region to look for water. Water has absorption features in this region. And so here we have a panel on the left, the 2 black and white ones, and the panel on the right, the color images. The panel on the left is Europa. They're all Europa. The panel on the left is the albedo. That's the brightness. And so you can see that there's some darker materials. The darker spots are basically those lines and the chaos regions that you could see in the reddish images from earlier. And the one on the right is basically using information from the spectrometer to determine composition. And so we have here a relative scale of the amount of ice versus non-ice components. So everything on Europa looks a lot like water ice. Even the quote non-icy material, it has water features. So that tells us that it's some sort of hydrated mineral, even if it's not just pure water ice. So here you can see the amount of non-ice material, 100% would be 1 here. The non-ice material lines up very well with the darker regions and these lines that we see in our visible images. So looking at the spectra and trying to understand what the minerals are, we have a few different spectra here. So on the right is a bunch of different sulfate salts and brines. A brine would be a frozen saltwater mixture. So we have different types of sodium sulfate, magnesium sulfate, and then the bottom of both images we have this Europa non-icy material. So we're still trying to figure out what what exactly is that non-icy material, because that's going to give us a clue into the interaction between the crust and the subsurface ocean. So you can see that on the right, maybe there's similar features, but none of them look quite right. So I looked at some other different salts, chlorine salts, and you might be familiar with NaCl, that's common table salt, and some other chloride salts, and froze them as brines and looked at their spectra to see how they compare to this Europa non-icy material. And you can see that the wavelength features actually line up. If we follow the lines here, they line up pretty well. Maybe the shapes aren't quite perfect though, so we're still trying to figure that out. And trying to decide or figure out what salts are actually present on Europa, it's hard because a lot of the reference spectra doesn't exist for the types of materials that would actually be on Europa's surface. Because of the temperatures, we have to make sure to measure the material at the appropriate temperature. So Europa is on average about 100 Kelvin. Water freezes at 273 Kelvin. Average Earth temperature is about 300 Kelvin. So this is pretty cold. And there's a lot of water there. So you have water that could make a higher hydration form. However, you also have radiation, which could break the bonds and maybe become a lower hydration state, or break the chlorine off, or the sulfur or sodium. So we really need to use our laboratory setups to accurately measure the spectra of materials under the right conditions. And it's really important to distinguish between these different salts too, because chlorine salts typically have a lower freezing temperature than sulfates or carbonates. What that would mean is if we find sulfates on the surface, or an indication that the ocean is sulfate rich, it probably means it's a warmer ocean and a thinner ice crust. So there might be an easier exchange between the crust and the subsurface ocean. However, if we find chlorides, it might mean a colder ocean and a thicker ice crust. Now, this is based on modeling. And of course, there's gradients between those two extremes, and there could be a mixture of different salts, but that's really what we want to figure out. So some ground-based observations of Europa include the Very Large Telescope and the SINFONI instrument, which is again a near-infrared spectrometer. So Ligier et al. Used this instrument to map out the composition of Europa, and they used my laboratory data that I showed earlier and put it into a model to try and determine what the composition was of the surface. And so here's a visible image of Europa, and so you can see here this is around 300 longitude, and so this is that darker material, and so this is where that kind of black outline of what we would call the chaos regions. And you can see that the chlorine salts, magnesium chlorine salts in particular, tend to line up with those chaos regions. And so you can see that we're up to almost 35% of the material in these regions could be magnesium chlorine salts. And so I mentioned that Juno was designed to study Jupiter, but they've tried to look at Europa too. So they do not have a near-infrared spectrometer, but they do have the infrared auroral mapper, which goes from 2 to 5 microns, so a little bit further in wavelength range and more into the infrared. But you can see here they have the spectra from it. We have NIMS, which is the Galileo near-infrared spectrometer. Also went out to this wavelength range, and compared it to a few different observations that Juno took of Europa. And so we can see that there's some nice big water bands. Again, if we compare it to the laboratory spectra, we have a really big water band at 2.0 microns here, and this is where we're seeing this water band here. And then it comes down, and so One of the things that we would really like to do is build a complete reference library that looks at all the different types of salts, all the different hydration states, and extend the wavelength range that we have for them too, because a lot of it has been focused in the near infrared, but we can see that some interesting things are happening at longer wavelength regions and also shorter wavelength regions. What I'm working on currently is using Lowell Discovery Telescope and a couple different instruments, the near infrared high throughput spectrograph, or NITES. That's again that near infrared region 1 to 2.4 microns, and the extreme precision spectrometer, or EXPRESS, and that looks at the visible wavelength regions. And it's actually an interesting wavelength range because we think that you can find color centers. So salts, when they're irradiated, become a pinkish color, which might explain that reddish material, or why it looks reddish in the visible images. So to summarize, and then I'll take questions, Europa, its non-icy component likely includes chlorine salts and sulfate salts probably. Salts have also been detected across the solar system. Mars is, of course, a good example of that. But also small planetary bodies such as Enceladus and Ceres. And it's really important to differentiate salts to understand the stability of water and, in turn, its habitability. Thank you. So we already have a few questions that I'll go ahead and get straight to those. Corey Cody asked, what is the source of the radiation? Right, so that's a great question. Jupiter has a very intense magnetosphere and radiation environment. So there are high energy electrons and protons and even neutral ions, neutral atoms that are coming off of the, following the radiation lines of Jupiter. And it's spinning, actually, the magnetic field is spinning faster than the moons are orbiting. And so it's actually very interesting because it's the trailing hemisphere that has most of the radiation damage of Europa. So as Europa is orbiting around Jupiter, the magnetic field is actually orbiting faster. And so it's slamming all the high energy radiation into the back of Europa. Another source of these neutral ions is Io. So Io, of course, is volcanically active, and it's spewing sulfur dioxide. That gets picked up by Jupiter's magnetic field, and that slams into Europa as well. So that is a potential source of the sulfur. And that's actually another really important reason to distinguish it between the sulfate salts and the chlorine salts, because if it's sulfate salts and it's on the trailing hemisphere, it might be that the sulfur is implanting exogenously to Europa. So, and that's actually also the reason why Europa Clipper will not actually orbit Europa. It'll be orbiting Jupiter in a very high orbit so that it flies by Europa continuously, but it's not just orbiting Europa because the high radiation environment is really tough on spacecraft missions and instruments. Okay, Rohit Takar asks, how did you figure out that it's water ice on the moon but not CO2 ice? So we used these spectrometers looking at our different wavelength regions. So we knew that there's water ice on Europa a long time, even before the pioneers went using ground-based telescopes and spectrometers. We can see, we can use Hubble, we can use ground-based stuff, we fly by, and we can look at the spectra and tell what mineral and or ice is present based on that. So we're pretty confident, we're sure that it is water ice and not CO2 ice on Europa. Bruce Morrow asks, are we doing any of the lab work on the ices at NAU? I'm not currently doing Europa lab work at NAU. I do work on ices at NAU though. That includes things like methane ice, nitrogen ice. So thinking about it in terms of further outer solar system bodies, Titan, looking at the lakes and seas of Titan, the liquids and the ices that form in those. looking at Pluto, CO, N2, methane, methanol. So we're looking at different ices for a lot of the icy outer solar system bodies at NAU. Any other questions? Okay, well, I'll stop sharing and we can get Emery back on. And if there's any last questions, otherwise, okay, great. No other questions for the moment. So thanks everyone, and have a great evening.
Thanks, Dr. Hanley. So as we can see, still lots of research going on here at Lowell Observatory, both with ices and all sorts of things that happen out there in the outer solar system. So this brings us to the next portion of our stream, which will involve a little bit of our interactive stargazing. So this actually brings up a pretty good point that using that same Clark telescope, the one that is giving us that live Jupiter cam in the top right of our screen, using that same telescope a couple of nights ago, we were able to capture a time lapse of those same moons moving around just like that Juno spacecraft was able to. So if we could load up that movie that shows it's just a brief clip, about 6 seconds, and the moon's taken with one of our other telescopes. But either way, we'll get a chance to see just some of the things that our public program can do in that respect. Now we are looking at that live view of Jupiter. It's not necessarily the clearest view that you could ever have, but that is something that happens pretty often in astronomy. We're looking through about 100 miles of atmosphere, and of course some of that changing in air pockets is going to give us a little bit of trouble when we're trying to view something that's over 500 million miles away. So we'll go ahead and watch that video of our moons going around Jupiter. So just like we saw before, Europa went around Jupiter and got lost in its shadow from the sun. Well, in this case, we're actually viewing Jupiter from an edge-on view. So you'll see Jupiter in the center with its moons going around the outsides, and there will actually be moons popping in and out from behind and in front of Jupiter. So just a little bit more of that idea. If you were to think about, Jupiter's system at opposition, that would mean that each of those moons would be on the same side of Jupiter, trailing off. Now this was actually taken using one of our telescopes at the Giovale Open Deck Observatory, which is what we will be using to do our interactive stargazing. And so I will go ahead and kind of jump right into that. And there we go, we're screen sharing. So we have a current view of Jupiter, not just through the Clark telescope, but a very similar view to what we just saw in that video. So as soon as this picture comes up and you see all of these kind of boxes and menus on the sides of it, that means that we are looking through our Cam, our plane wave telescope setup. So yeah, I see that it's on our screen. We've got Jupiter with 2 of its moons on the right, and then a moon up and to the left, and then very far to the left. We also have the ability. Oh yeah, so there's just some of the technology that we use to move that around. So we could even zoom in on Jupiter a little bit and actually decrease our gain or our exposure time, and that will make the moons disappear, but we will be able to see a little bit of the stripes on Jupiter. So that's what we're viewing now. Again, you'll notice that those two moons that were just off to the right, those have completely disappeared. And so there is kind of a trade-off when you're doing certain types of research. Do you want to look at the planet, or do you want to look at the moons off to the side? And this is actually something that, as you can see, our exposure time is all the way down to the milliseconds. Without very much digital gain, which means that this is actually something you can see with your eye. If you go out tonight, it's going to be the brightest thing in the southeast region of our sky. During our live stream, actually, the ISS passed right overhead. And so that was a good chance to see something with your eyes. But if you just take a pair of binoculars, same kind that you would use for bird watching, you can actually point those up at Jupiter and you'll catch this really big bright object in the middle with its moons all splayed out to the sides. So anytime tonight, if you have the chance and you have the resources, definitely take a look at Jupiter through your own binoculars. Now, I see that we have a question that Io is supposed to be transiting Jupiter tonight. That is something that you would see through a telescope. So if we bring our gain back up just a little bit, you would actually see those moons that are off to the sides. Those will be changing positions as the night goes on. And that is really what the basis of Galileo's discovery about moons going around Jupiter instead of everything just being based on going around the Earth. You have this discovery that there are these things moving around in our outer solar system. So we'll go ahead and take one of our first questions, which is, can we see Thuban or Bellatrix? And I believe that Thuban is visible right now. Now with our telescope, when looking at a star, these are going to be very bright objects. Yeah, so we see that's in the constellation of Draco, just between the Big and Little Dipper. Right now our telescope is moving over there, and you've got that bright star coming into view there. Again, with that atmospheric haze, it's causing a lot of that twinkling to appear. If you had the eyes of a telescope, yes, you would be able to see the air currents pushing that around. But when we're sitting here, you can actually notice that change in brightness as the twinkling of a star. And so when you get something big like Jupiter, it actually takes up an appreciable size of the camera's view. And so even though the edges might be a little bit wavy and blurry, something that we can see on our live Jupiter cam at the top right, you'll actually see that the star as a point source is getting its light all changing, from its path through our atmosphere. So I see that Rohit Takar says, what is the Jupiter live cam and why are the images opposite to each other from the Godo? And yeah, we do have a mirror that's operating this first telescope that's looking at Thuban. So it's a type of telescope that has a mirror at the very base. All that light comes in, gets bounced to a camera, and that's how our image is gathered. When you're talking about the Clark telescope, this is a very historic instrument, 120 years old. And so before they had the technology to make these great mirrors, they were actually hand carving lenses out of glass. And so you're actually viewing a more of a proper view of Jupiter through our live cam and more of a reflective view of Jupiter through our other telescope. So those would just be kind of an artifact of the type of telescope that we're using. Now, the ISS did set. Unfortunately, it was right during the moment that Dr. Hanley was giving her talk. And again, with the comet that just sets in about this time of night, and it's going to be closer toward the north. And so you're going to want to come out maybe right around dusk and get a nice open view of the north, where no mountains or trees are in the way, and that would be a great way to see NEO-wise. From here, we can go ahead and look at Saturn. So that's going to be just next to Jupiter. We'll go ahead and move our telescope all the way back down to the southeast sky, so we can see in our little image there that Jupiter and Saturn are right next to each other. And if you were to go outside tonight, you would actually be able to notice that same thing in the sky. You'd be able to look up and see both Jupiter and Saturn in the sky together. So here we have Saturn with its rings. As you can imagine, back in Galileo's time, it was sort of hard to distinguish what was actually going on here. You have an oval type object, obviously something bright in the middle, two brighter bands on the outer sides. Galileo was under the impression that this was 3 different objects, that it was maybe a planet with 2 moons on each side. And then went into all sorts of different iterations. Some astronomers drawing it more like an eye, which you can kind of imagine. And then again, just like we did with Jupiter, we would actually be able to notice some of Saturn's moons if we up our gain and exposure time. So this might be what you see looking through a telescope, but now that we've really brought up that exposure time, each of those little points, which do line up with the rings of Saturn, are going to be moons for the most part. And so and without a reference guide, it is unfortunately hard to tell exactly which ones are moons and stars, but likely that brighter object on the bottom left is going to be Titan that you're seeing with that mouse. And then you have things like Mimas and Enceladus, one of the moons that Dr. Hanley mentioned with some water and ice on it. We're actually seeing some of those moons too. Now, because Jupiter and Saturn are right next to each other in the sky, if Jupiter is at opposition today and in this past week, Pluto is also at opposition, and Saturn, trailing close behind, is actually going to be at opposition, I think, next Saturday. And so we'll go ahead and have another one of these events Monday night, next Monday night, and we'll have Dr. Hanley feature some of her research on Titan, that moon that I mentioned off to the side. And so definitely tune back in for some of our future events. Now we have just a couple minutes more of our interactive stargazing. If there are any requests, definitely send those in right now. If not, I would like to pull up some pictures of Pluto that we took. And actually, if we could, still within the Malincam software, if we could move our telescope to where Pluto is, it'll be just between Jupiter and Saturn. So you might zoom in there. Yep, there's Pluto. So we can move our telescope to there, get an idea. Now this object, Pluto, you have to imagine it's smaller than the Earth's moon, and it's about 4.3 billion miles out there in the solar system. And so needless to say, it's not very bright. So we're definitely going to want to kind of bring up our exposure times and gain. So here we are with a nice view of Pluto. We have images that were taken. So just sitting right here, we're looking for Pluto. in this huge star field. And you can imagine how hard it might be to identify, what's a planet, what's a star. There's just a lot of points of light here. But what you can do is changing the view from one night to another. You can start to recognize the patterns that the stars make, but a planet passing through the solar system will actually move among those groups of stars. So it's definitely helpful to try and build some patterns into the positions of those stars. But the flipping of images that we're showing right now is actually showing Pluto passing from one point to another. So you can see that the stars are all staying put. The background might change a little bit, go from slightly darker to slightly lighter, but we can go ahead and be transitioning between those images. Now, we can point the mouse over where Pluto is, and you can just get an idea that over just a couple of days, this might have been less than a week, you're actually seeing Pluto travel a pretty appreciable distance in our image. And so this was all done back in the early 1920s and 1930s using glass plates and emulsion film on those glass plates. That will be a video, that will be featured in our video by Kevin Schindler coming up in just a moment here. So we're going to go ahead and kind of transition into Kevin Schindler's video. We'll be seeing the Clark telescope as it is, and we'll be seeing it during the daytime. So keep in mind that view of Jupiter is coming from that telescope that Kevin Schindler's standing next to. He's going to point out an image of Jupiter that was taken through the Clark telescope, an old camera that was down there. And in fact, we're going to go to one more object. We're going to go to Albireo during our interactive stargazing. And so this will be a really awesome thing. This is another group of stars, and we'll go ahead and look at it. Now, these two stars, one of them is very similar in composition and age to the sun. The other one is a lot bigger and brighter than the sun. And so we have that more blue colored star to the bottom right, representing a younger, hotter star. That orange star, which appears a little bit more white in our view here, is going to be a star very similar to our sun, maybe a little bit larger and older, but it's giving off this cooler color, closer to the red and orange side of the spectrum than those bright, hot stars like that blue to the bottom right. So that's, definitely something that we can see using our interactive stargazing, looking up into the sky. There are all sorts of gems scattered throughout the sky. You have these double stars, you have planets. Almost anywhere you point a telescope, you could find something very spectacular. So we are going to continue with another round of interactive stargazing after we talk about that video and the discovery of Pluto. We will get a chance to go ahead and look at some of the other objects. For example, NGC 4565, we will be looking at a galaxy or two. So definitely stay tuned in for that. But without further ado, we can go ahead and play that video by Kevin Schindler. Again, focus on that Clark telescope. That's the one that you're looking at Jupiter through, and the photos that were taken of Jupiter. So we'll go ahead and roll right into that.
Here we are at the historic 24-inch refracting telescope at Lowell Observatory, built by Alvin Clark and Sons. 32 feet long, 24 inches in diameter, one of the best telescopes of this type ever made and used. And this is a great place to talk about planetary work, because this exquisite instrument allowed Percival Lowell and other astronomers here at Lowell Observatory to really unravel some of the mysteries of the universe. Percival Lowell first got this telescope in 1896. 2 years after he opened the observatory here, he had borrowed a couple telescopes initially until he could have this masterpiece built. And we look at it today, and it really is a piece of art, but it also is such an important piece of astronomical history because of so much research that was done with it. So this is a great place to talk about planets at Lowell Observatory. And of course, we remember the name Percival Lowell. He's the one that started the observatory. He's the one that wrote so many compelling books about the ideas of life on Mars. He's the one that hired many other astronomers to help him out. And you think of the legacy of Percival Lowell. One legacy was just building the observatory. Another was a search for a ninth planet, which eventually, after his death, led to the discovery of Pluto. Another one of his legacies was hiring excellent staff to help him with his research and then continue in their own directions. One of these was V.M. Slifer. V.M. Slifer came from a large family in Indiana, went to Indiana University, and using this telescope with an instrument called a spectrograph, he detected the first evidence of the expanding nature of the universe. And that really fundamentally changed the field of astronomy, because it told us that space was much larger and much vaster than we previously thought. So this was around 1912, 1913, that he was starting to make these discoveries. So V.M. Slifer was one of the important early astronomers here, but another one has a familiar name. His name is E.C. Slifer. And E.C. Slifer was V.M.'s younger brother, also went to Indiana University, and he started his association here at Lowell Observatory in 1906, not to study Mars, which he would do eventually, but to help Percival Lowell on a project that was kind of quiet at the time. And that was a planet that Percival Lowell believed was out there, he called Planet X. So some of his earliest searches for this supposed Planet X was helped out by E.C. Slifer. E.C. Slifer had a kind of a scholarship to come here for a couple of years and help with the search. It was called the Lowell Fellowship. So he came here, helped with the search for Planet X, which years later eventually culminated in discovering Pluto 25 years later. But 1906, E.C. Slifer is just helping out in the early stages of the search. Percival Lowell really liked him, really liked his research, and said, why don't you just come here and work here permanently alongside your brother? And so both brothers spent their entire professional careers here in the observatory, and both of them made fundamental contributions using this telescope and different instruments attached to it. While V.M. Slifer was using a spectrograph, which allows you to look at light gathered from space and break it down into its individual color or individual wavelengths and see what things in space are made of and how they're moving and such. E.C. Slifer focused on photography. When we think about photography of astronomical objects back in the early 1900s, it was pretty rustic. The film they used, the emulsions were really grainy. There was still a lot to be done with developing techniques. So E.C. Slifer came along. He built a lot of different telescopes, and he tested these telescopes. After he was done helping with the search for Planet X, he really focused on photographing Mars. And he photographed Jupiter and Venus and Saturn, photographed most of the planets, especially Mars and a lot of Jupiter. And he developed techniques that are fundamental to astrophotography today, because back in his day, there was a new technique of what we would consider today stacking, where you take, instead of taking an individual picture, you take several in a row right after each other, and then assemble them all together. And by doing that, you're able to get rid of some of that noise and get really crisp, clear images, at least for the time. So by using different cameras and different filters, red filters and blue and yellow and so on, and using different types of film and emulsions, and different plates, because when I say plate, those are photographic plates. To take a picture, using this telescope, for instance, you would take this eyepiece assembly off and stick a camera on the end. These cameras can be really long, and we'll take a look at one in a few minutes. And then inside that camera, you would insert in a kind of a carriage, a holder, a glass plate. And this glass plate has emulsion on one side. That's how you would capture the image. So with the camera attached here, with a plate down here, of course it's all done in the dark, because you don't want to ruin the exposure. So you're kind of fumbling around doing this. So to take the picture, you move the telescope on Jupiter, for instance, and once it's all set up, open the shutters, and for an hour, maybe it's only 10 minutes, maybe it's 3 hours. The exposure times he experimented with, he would capture this image. The shutters open that entire time. And so during that time, he has to stand here and use one of these other telescopes and guide the telescope. Look through that to make sure the telescope's moving at the right speed to stay focused on an object, otherwise you're going to get a fuzzy image. So this was really tedious work, and it required thousands of hours of work, and E.C. Slifer spent decades doing this, using this telescope, using telescopes in South Africa. He went on several expeditions, one in Peru. So he used telescopes around the world, but this was the primary one he used. And by using the cameras and experimenting with different techniques, he really established this idea of stacking for astronomy, which is important for astronomers today. So he, at one point, took more images of Mars than anybody else in the world. And he also captured many images of Jupiter. And before his career was ended, he gathered some of these images into a couple different books. And today we're able to easily look at these things and just see what the state of astrophotography was 100 plus years ago and how much he contributed to it. What we're doing today really was influenced by the work that E.C. Slifer did on Mars and Jupiter and so on. So this is the telescope he used. Let's take a look over here at one of the cameras he used that attached to this telescope. I'm standing about a dozen feet away from the telescope, the 24-inch Clark telescope, kind of on the northeast wall of the dome. And embedded within the wall are several different display cases. This one is really important to today's discussion because it has some of the books that E.C. Slifer wrote and one of his images of Jupiter. And then down below here is one of the cameras he used to take these planetary pictures. And when you think about cameras today, astronomers, are sitting at a computer and you have charged coupled devices, CCDs, attached, in a computer system that captures images digitally. This is the old way they did it. This end of the tube of the camera would go into the butt end of the telescope. So instead of looking through an eyepiece of the telescope, this would go in. And then down here is the plate holder. One of these photographic glass plates would be held into that carriage. So for instance, something you get the idea, that would go inside that plate carriage. And of course, this has to all be done in the dark because these plates, they're pieces of film. They have emulsion on one side, they have to be kept in the dark. So there's a lot of fumbling around to make this contraption work. But by using this, E.C. Slifer, not only used this camera, but he built other cameras also. And he tried different types of photographic glass plates, different emulsions. He used a lot of different filters on the telescope to get the final product of these really, for the time, very detailed images of the planets. And Jupiter is one of those that he captured. We have a couple comparative images of Jupiter here. And again, when we think about the time, and photography wasn't very well developed, the emulsions were really grainy. And so this new technique he adapted into astronomy that we think of today as stacking, where you take a bunch of images in quick succession and then put them all together, and that allows you to get rid of some of that noise, some of that junk you get on the emulsion. And it allowed him to get some of the best pictures of planets at the time, including Jupiter. And so today, I think it's really a fun thing to be able to get some of these pictures he captured and look through telescopes, especially when Jupiter, for instance, is at the same position, and compare those images that he took versus the view. And it really is pretty remarkable what he was able to accomplish back then. I'm back here next to the 24-inch Clark telescope, where the story of planetary photography at Lowell Observatory started, and also where I started talking about E.C. Schleifer's contributions just a few minutes ago. And this seems like a good place to end also. And looking back at E.C. Schleifer and his contributions, we remember the name Percival Lowell for his planetary work, his ideas about life on Mars, his dogged pursuit to find a ninth planet, and eventually led to the discovery of Pluto. But we have to remember those other scientists who made really important contributions themselves. E.C. Schleifer was critical to the development of astrophotography. With this telescope, and some others, but mostly this telescope, he used different cameras, different filters, different exposure times, different emulsions, to test over and over, night after night, thousands of hours, photographing Jupiter and Mars, and looking at how these photographs were captured, making little adjustments night after night until they really refined this photography technique and captured the best images of planets of the time. And so we really owe him a debt of gratitude for all the work he did and how he was able to advance astronomy. And it really, again, is a point of one of those things of Lowell Observatory that we know some of the big discoveries like Pluto, the expanding universe, and so on, but there's so much else in the Lowell story, and that goes back to the people and their pursuit for excellence, night after night, sitting in a dome, just to try to do the best they can with what they do. Just like E.C. Schleifer pursued excellence and took some of the best planetary photographs of his time, our modern-day astronomers continue that legacy of excellence, looking out into the solar system and beyond, and trying to unravel the wonders of the universe.
All right, so now that we've seen that Clark telescope in person, that's again the one giving us that live Jupiter cam, we can go back into our interactive stargazing and continue with that for the rest of the night. So we'll get another 15 minutes of that, bringing us to the total half hour. I'd like to first bring us to an object called NGC. Let's see. It's called the Needle Galaxy, NGC 4565. And as you can see here, it is one of those galaxies. So all those stars in the foreground are actually in between us and that distant galaxy. So you can imagine that all those little points are somewhere in the Milky Way, and we're actually looking far beyond all of that. And so we can also look at that in an inverted image. And this is actually going to show us a little bit more of that detail of that core. So that bright, dark spot that you see toward the center will be the core of that galaxy, with a little bit of what we call a dust lane in front of it. We did have a question earlier asking why planets and galaxies tend to be sort of planar like this. So just to recap, our solar system lies in one plane. Galaxies often lie in a plane like this as well. That's because things tend to spin when they're in outer space. And so that spin allows those objects to kind of flatten out. You can almost think about it like a ball of pizza dough. And if you spin that quickly enough, it will flatten out and become one of those larger things. If you want to get more technical about it, we call it the law of conservation of momentum. So all that angular momentum, that spin, is getting translated into the lowest possible energy state, which just tends to align everything very well in that line. So with that being said, we have that galaxy view. We can actually go to another group of galaxies. So this is going to be called NGC 7317. We had a request for that earlier. And we're going to go ahead and look at this. It's a little bit lower on our sky. So as you watch the telescope move on that, you'll see that the telescope, again, is kind of toward the lower eastern sky. And so just like Jupiter, we are going to be looking through a lot of atmospheric haze. Now that first image that's popping up is just an artifact of the live view that we're seeing. The camera was actually moving while that picture was being taken. And so the bright streaks you see are some of the brightest stars showing up over that long exposure. If you're counting the seconds at the very bottom of the screen, you can see that our exposure time right now is about 4 seconds out of 23 and a half. And so we're getting lots and lots of light, including some of the sky glow of Flagstaff. And so that's kind of why you see a lot less of a stark difference between the stars in the background. But zooming in, yeah, right there toward the middle, those kind of cloudy and nebulous objects are actually going to be galaxies. We could maybe try turning up the gamma, and that would reduce our background glare, but it's still not much you can do on a night like this and in a city like Flagstaff. Now, one thing to talk about real quick about Flagstaff is that we do have a lot of laws in place to limit the amount of light pollution that's going on. Yeah, as we can see, that gamma helped it a little bit, but still, anytime that you have a city and any lights going up into the sky, it is going to make it harder to practice this astronomy. So from here, I did get a question about the Andromeda galaxy, which unfortunately is not up in the sky right now. We can look at Maki Maki, which is another one of our dwarf planets. And so we can go ahead, kind of switch gears back into that planetary mindset. So this is going to be something, again, within our own solar system. You've looked at 2 galaxies, both on the order of millions of light years away. So that means it takes millions of years for the light to reach us from those distant objects. When we look at these more solar system objects, it may take a few minutes, a few hours, maybe a few days for that light to reach us, but definitely not the millions of years that it takes from another galaxy. So unfortunately, we did get a request for the Kappa Ursa Majoris star system. We can't actually see that one because it's behind the dome. There was another question about 3 star systems, something like Centaurus, the one that carries that star that's closest to the Earth, Proxima Centauri. Unfortunately, that one is inaccessible at this latitude as well. We're too high up on the Earth to see it, and so the ground gets in the way before we would actually be able to see Now I see a question just popped up. Why do I refer to magnitude? So magnitude is going to be the brightness of an object. Maki is going to be magnitude, maybe something like 11 or 12, which means it's almost about 1 trillion times fainter than some of the stuff, some of the other stuff that we can see in the sky. So it definitely takes a lot of technology, a lot of software to be able to gather that little bit of light. In fact, so Maki is going to be somewhere in the star field. A little unclear whether our telescope actually has the ability to see that. If we turn the exposure up a little bit, we'd be able to see more of those stars in the background. But I've just been informed Maki is magnitude 16. So again, something really, really faint, really discovered pretty recently compared to Pluto. There's another dwarf planet while we're on the subject. So Pluto, Maki, those are part of the dwarf planets in the outer solar system. But we have another one called Ceres, which was actually discovered in the early 1800s within the asteroid belt. And that one wasn't quite large enough to be considered its own planet, but it had been for a very small amount of time. So we had, the same system, the same situation happened with Pluto. We have something that was a planet that got demoted from that status once more information came out. That's the same thing that happened to Pluto. And for those wondering at home, why Pluto is no longer considered a planet. Now, the magnification on this telescope is actually going to be constant. I believe it's something like around the 180 to 200 times magnified region. So we're taking a relatively small area of the night sky, maybe about the size of your pinky finger, and we're blowing it up to fill this entire screen. So definitely quite a bit of magnification here. So we'll go ahead and look at some of the other things that we've been requested. M57 is an awesome object called the Ring Nebula that's up in the western sky right now. In fact, last time the observatory was open, we were able to catch the Ring Nebula at the very end of the night. And so it's kind of funny that the timing of this whole pandemic has given that object back to us. So we'll talk about the Ring Nebula. This should be a relatively short exposure time. And yeah, there we have that beautiful Ring Nebula right in the center there. This is going to be a system very similar to our solar system, except fast forwarded about 4 billion years into the future, where that sun, that star in the center, has kind of gone through most of its life process, burned up a lot of the helium and hydrogen at its core, and started expanding. And it's basically giving off these big bursts of gas into outer space. And those are slowly radiating outward, taking up more and more space. And the structure that you see right here is about 1 light year across, so about 6 trillion miles from one edge of that ring to the other. So a very impressive thing. Someday the sun will go through the same process. And what's really amazing is that when we look at these things, we're capturing this image, something that only happens for about 20,000 years before all that gas disappears and is no longer visible. And it's something that happens often enough for us to still be able to see it happening hundreds of other places in our Milky Way galaxy. So there was another request for the Andromeda galaxy, which unfortunately is not up right now either. I see we have the Cat's Eye Nebula. Actually here, let's go ahead and address that question about the 3 star systems. We could go to Delta Cygnus. So that's going to be right next to where we looked at Albireo and also this Ring Nebula. This is going to be a triple system of stars. Now, sometimes what happens when we're looking at systems of stars like this is that you really only see one point of light. And as astronomy continues to advance, we've actually been able to split more than just visual binaries. There's a method called spectroscopic binary measurement, and we can actually see overlapping signs of chemicals on those stars. And that's actually going to tell us that there's two stars right next to each other. One more, we can look at the Cat's Eye Nebula. And this is going to be a really impressive object, another one of those planetary nebula. So remember that these objects are pretty short-lived. It's really incredible that we're able to see any of them at all, and so many of them throughout our whole sky. So we have a request for the Crab Nebula, which unfortunately is down below the horizon for us right now in the constellation of Taurus, but we would be able to get that one closer toward maybe the winter time. So I see in the comments there's another comment about the triple star and the Big Dipper. The middle handle star is called Mizar, but it's also known as Mizar and Alcor. And so if you were to go outside and look at this on a good night, you might actually be able to see the central points of light and then that bottom right point of light as two separate objects. So remember, we're at about 180 times magnification. And so the great separation that you see between the central object and that bottom right star is really only going to look like a tiny sliver in our night sky. They might appear to be about the width of I don't know, a BB, a small pellet, apart from each other. And if you have very good vision, you'll actually be able to separate these two stars from each other in the night sky. Now we zoomed in on this, and you can see that that central point of light is actually a binary star. So we've got 2 points of light that are both radiating from that place. And again, that means that there's two stars in that solar system, maybe planets going around each of them. Now we'll go ahead and go all the way back to Jupiter for kind of one of our final objects for the interactive stargazing. I do want to thank everyone for tuning in and go put your input. There's one more question I want to address, and that was from Lee, and we're talking about life on other planets, or that we're under a dome. So two separate questions. With the Giovale Open Deck Observatory, the roof actually slides back, and so it's not under a dome during use, but it is under a roof during the daytime. In terms of life on other planets, that's not something that we have ever discovered definitively, but all the signs and kind of possibilities are there. If you tuned into Dr. Hanley's talk, she mentioned a lot of water, a lot of water present on that moon Europa. So that is one of the first places that we're expecting to really search for life a lot. I did see one more question just about Comet Neowise. That is something that we are not able to see right now in the sky, but if you go out around dusk, just after the sun sets and as the stars start to pop out, it's going to be in the northern part of the sky. Something great for you to look at just with your own eyes, or even take that pair of binoculars. Again, that's going to give you great views of Jupiter and its moons, give you great views of Saturn, and even give you a little bit more detail on that comet. So those instruments, those binoculars that we have today are probably rival the telescope that Galileo use to discover these moons around Jupiter. So definitely don't forget that we're living in a great point in technology where, you know, some of these things that you had to really try for back in the day, they're just kind of at our fingertips. So for in terms of that, I think that's a pretty good wrap up. I see that we've hit most of the objects. One more request I see, we have Epsilon Lyrae. So we could go to another binary star in the constellation of Lyra, and we'll probably end on that. So yeah, we're zooming in on Lyra. The ring nebula M57 that we looked at is actually in the same constellation too. And then we're zooming in on a binary star. So again, two separate points of light that if you were to look up here with just your eyes, you would see a single point of light. And it wasn't until telescopes were invented that we really started to discover just how many of those stars are multi-star systems. If you think about the sun and our one star, we're kind of the minority, with up to about 70% of all those other stars out there being part of multi-star systems. So with that, that can pretty much conclude our interactive stargazing and the program of Jupiter's and Pluto's opposition. So I want to thank everyone very much for tuning in. We can stop our live view of this streaming platform and go back to that view that we're getting of Jupiter through our Clark telescope. Again, I want to encourage anyone who gets the chance to come up to Lowell Observatory and take a look through some of these telescopes, get a chance to come up and look at some of these historic places. Once we open back up, definitely tune in to the Saturn live stream on next Monday, which will be very similar to this, just all focusing on Saturn, but it will feature some talks from our astronomers and a little bit more interactive stargazing. So thanks everyone. Definitely stay tuned to Lowell Observatory for all of your needs, space related. And I hope everyone has a wonderful night, or as we saw in Sri Lanka, a wonderful day. So thanks everyone.